Second order systems given below. G of s is equal to 10 over 1 plus 2s multiplied by 1 plus 0.33s. The given system is in the form of pole 0. By substituting s equal to j omega, and we are going to convert the pole 0 form into time constant form. G of j omega is equal to 10 over 1 plus j2 omega multiplied by 1 plus j 0.33 omega. The corner frequencies are 0.5, 3 radian per second. Now, forming the tabular column and writing the terms based on the corner frequency, that is in ascending order of the corner frequency. So 10 is a constant, that is the first term, and the first corner frequency is 0.5, and the related term is 1 by 1 plus 2s. Second corner frequency is 3, and the corresponding term is 1 by 1 plus 0.33 s. Now the first term is 10, which doesn't have any slope and which doesn't have any corner frequency. No corner frequency, no slope, no change in the slope. And the second term is 1 by 1 plus 2s, which contributes the slope of 20 dB per decade, and the corner frequency is 0.5, and the change in slope is 20 dB minus 20 dB per decade. Third term is 1 by 1 plus 0.33 s. The slope is minus 20 dB per decade, and the corner frequency is 3, and the change in slope is minus 40 dB per decade. Now moving on to the next slide. Phase angle of the G of j omega. It is given by minus tan inverse of 2 omega minus tan inverse of 0.33 omega. That is real part divided tan inverse of real part The phase angle of G of j omega is found out by the equation minus tan inverse of imaginary part divided by real part. Here in this 1 plus 2s, that is 1 plus j2 omega, the imaginary part is 2 omega and the real part is 1. So no need to write. 2 omega divided by 1, that gives 2 omega. So the phase angle is minus tan inverse of 2 omega minus tan inverse of 0.33 omega divided by 1. So now selecting the angular frequency omega below the corner frequency and above the corner frequency and in between the two corner frequency. Here the two corner frequencies are 0.5, 0.5 and 3. So we have considered the angular frequency omega below the first corner frequency 0.5. So we have taken 0.1, and in between the two corner frequency 1. Above the corner frequency we have considered 10 radian per second, 30 radian per second and 100 radian per second. So we have considered the corner frequencies below and above and in between the two corner frequencies. And substituting the value of omega in the phase angle formula, we are getting the phase angle minus 11.489. For 0.1 we are getting minus 11.489. For 0.5 minus 54.369. For 1 it is minus 81.69. For 3, minus 125.24. For 10, it is minus 160.279. For 30, it is minus 173.217. And for 100, we are getting the phase angle of minus 177.971. Moving on to the next slide, it is the magnitude plot of the given transfer function g of s. First, we have marked the corner frequencies CF1 and CF2 in the given semi-log sheet. Here, x-axis is logarithmic because 0.1 times 10 we get 1, 1 times 10 we get 10, 10 times 10 we get 100. So the x-axis is logarithmic axis and x-axis is the normal axis, linear axis. Okay, right. Now we have marked the corner frequencies CF1 and CF2. CF1 is 0.5 and CF2 is 3. And the purple lines are the reference slope, that is reference for minus 20 dB per decade. The purple line, this is the purple line, this is the minus 20 dB per decade, and here it is the minus 40 dB per decade. This is the reference. Per decade means the difference is 10 between 0.1 to 1. So 20 dB per decade. So I redraw the 20 dB per decade. This is the meaning. And another thing is 40 dB per decade. Here is 40 dB per decade. So this is the reference line, 20 dB per decade and 40 dB per decade. 20 log of 10 we get gain as 20 dB. So start horizontal line, the first term in the tabular column 10, that gives the gain of 20. So draw a horizontal line of 20 dB as a gain. This 20 dB flat line continues up to the first corner frequency, and at every corner frequency the slope of the magnitude plot will definitely change. So this first term 10 contributes the gain of 20. So it's a flat line, horizontal line, that is up to the first corner frequency. After the first corner frequency, that is 0.5, the slope will change. And the second term is 1 by 1 plus 2s. This term contributes the slope of minus 20 dB per decade. So from the first corner frequency up until to the second corner frequency, the slope will be 20 dB per decade. So moving a parallel line of the reference line 20 dB per decade, these two lines are parallel. So drawing from the first corner frequency, that is at 0.5 and 20 dB, draw a parallel line from first corner frequency and to the second corner frequency. And in the second corner frequency, that is at 3, again the slope changes, and the corresponding term is 1 divided by 1 plus 0.33 s. This term contributes only to minus 20 dB per decade. This minus 20 dB per decade is added with the previous slope, that is minus previous slope is also minus 20 dB per decade. So we get 40 dB as the resultant. 40 dB is the resulting slope. So drawing a parallel line with from the reference 40 dB per decade reference line from second corner frequency, these two lines are parallel, and these two lines are parallel. I hope you understand. Sorry, this 20 dB is parallel 20 dB minus 20 dB per decade line is parallel with this line, and this is the minus 40 dB per decade reference line, and it is parallel with the parallel to this line. Thus we have completed the magnitude plot of the given transfer function g of s equal to 10 divided by 1 plus 2s multiplied by 1 plus 0.33s. I hope this magnitude plot is easy for you, and we found the omega gc, that is gain crossover frequency, as 4 radian per second, because this is the magnitude plot, this is the magnitude plot, and this magnitude plot is crossing the 0 dB at the frequency omega gc. This is gain crossover frequency, which is 4 radian per second. Moving on to the next slide, phase angle plot of g of j omega. And in the semi-log sheet for the phase angle plot, x-axis is the linear axis, x-axis is the logarithmic axis, y-axis is the linear axis, and from the tabular column of phase angle we have to mark the coordinates, that is at 0.1 the phase angle is minus 11.4, at the omega equal to 0.5 the coordinate is minus 54.54. Similarly, locating all the coordinates in the semi-log sheet we get, and joining all the lines smoothly we get the phase angle plot of the given transfer function g of s. And omega gc, that is gain crossover frequency, is calculated as 4 radian per second. Draw a vertical line from the omega gain crossover frequency or at omega gc, and the phase margin is calculated as 47 degree, that is from the horizontal line of minus 180 degree, and from the gain crossover frequency 4 radian per second, draw a vertical line from minus 182 to the point where the vertical line meets. So this is the phase margin, which is found as 47 degree. So if you plot this phase angle you can able to calculate the phase margin as 47 degree. Similarly, theoretically also you can able to calculate the phase margin from the phase angle, that is phase angle formula. Substitute omega equal to 4 radian per second. You will be getting the phase margin closely to the 47 degrees. I hope this video is clear and will be helpful to face the examination, or you can draw on your own Bode plot of the given transfer function of a second order systems. Please support the channel to give you the better videos. So until we meet in another video, it's goodbye. Please don't forget to subscribe the channel Vidyar Kalai Winmin. Take care. Bye bye.